All right, let's dive in. Today we're going to talk about a technique in calculus that is frankly a total game changer. It's called implicit differentiation. It's a really clever way to find derivatives when your variables are all tangled up together.
So to really get why we need this, let me just ask you a question. How would you find the slope of a tangent line to a circle? I mean, it sounds simple enough, right? But if you try to use the differentiation methods you already know, you're going to hit a wall, and fast.
Okay, so before we tackle that circle, let's do a super quick review of what we'll call the old way, just working with regular explicit functions. This is probably how you first learned to take a derivative.
So you're used to seeing something like the function on the left, right? Y is all by itself. You plug in an x, you get a y. Simple. But look at the equation on the right for a circle. The x and y are all mixed up. They're related for sure, but y isn't neatly isolated.
So if you wanted to use our traditional methods on that circle equation, your first instinct would be to do a bunch of algebra to get y all by itself. And, not only is that an extra step, but it actually creates a much bigger headache.
And here's the headache. That one simple circle equation actually breaks apart into two totally separate functions. You get one for the top half of the circle and another for the bottom half. It's just clumsy. It means if you want to find the slope somewhere, you first have to figure out which of these two functions you're even talking about.
But this is where we get the big aha moment. What if there was a better way, a more elegant way? What if we could just skip that whole step of solving for y completely? And that's exactly what this new tool lets us do. It's called implicit differentiation, and it is perfectly designed for this kind of problem. So here's the core idea. We can find the derivative dy dx straight from that messy, mixed-up equation. The trick is to just assume that y is some function of x. We don't even need to know what it is, and then we just differentiate both sides of the equation piece by piece.
And the best part is, there's a clear roadmap for this every single time. First, you differentiate both sides. Now, step 2 is the absolute key. It's the secret sauce. Anytime you differentiate a term with a y in it, you have to use the chain rule. That means you tack on a dy dx at the end. After that, honestly, the calculus is over. The rest is just algebra. You gather up your dy dx terms and solve for them.
Okay, enough talk. Theory is one thing, but let's actually see this method work its magic. We're going to go right back to that circle problem and see just how clean the solution is.
All right, let's do this. Our mission is to find dy dx for the equation x squared plus y squared equals 25. No solving for y, no splitting it into two functions. We're going in direct.
Okay, let's go term by term. The derivative of x squared with respect to x, that's easy. It's just 2x. Now for the y squared term. This is where we use the chain rule. The derivative of y squared is 2y, but then we have to multiply by the derivative of the inside part, which is y. So we get 2y times dy dx. And on the other side of the equal sign, the derivative of a constant, 25, is just a big old 0.
And just like that, the hard part, the calculus, is over. Seriously, everything from here on out is just shuffling terms around. To get the dy dx term by itself, we'll just subtract 2x from both sides. And for the final step, we just divide by 2y to solve for dy dx. The 2's cancel out and look at that. Dy dx equals negative x over y. Isn't that beautiful? Instead of two complicated square root functions, we have one simple, elegant formula that gives us the slope at any point on the circle.
So yeah, it works great for a circle, but where this method really shines is with something truly gnarly. Take a look at this thing. It's called the folium of Descartes. Now, can you imagine trying to solve that equation for y? I mean, that would be an absolute nightmare.
And you don't have to take my word for it. The source material itself says that for curves like this, trying to do it the old way is just not easy. It says implicit differentiation saves an enormous amount of work. For these complex curves, it's not just a cute shortcut, it's pretty much the only practical way to find the derivative.
Okay, so let's zoom out and put a bow on this. Let's talk about why this technique is so important and what the big picture looks like. So what's the bottom line? Well, implicit differentiation is a huge deal because it lets us analyze a whole new class of problems. It's really just a clever application of the chain rule, and it lets us find rates of change even when we can't possibly solve for y. And yeah, the answer often has both x's and y's in it, but that makes total sense because for these curves, the slope at any point depends on both its x and y coordinates. And that leaves us with one final thought to chew on. We've just learned a powerful method for looking at systems where variables are deeply interconnected. So where else might this apply? What kind of complex relationships, maybe in physics or biology or even economics,
where one thing implicitly shapes another. Could this amazing tool help us understand?